Right, so this is going to be kind of odd talk. I'm going to try to explain why I'm even working on this problem. Okay, so the Department of Energy runs various data collection sites, and one of their programs is this atmospheric radiation measurement program, which has sites all over the world. But one of the main ones is in the Southern Great Plains of the United States. And there's a site at Lamont, Oklahoma, that for almost 30 years now has been measuring surface meteorology every minute. And so it's a kind of, I mean, hopefully from a meteorological perspective and perhaps from a radiative transport perspective, it's viewed as a real resource, although I don't know how much people really look at the data at the minute resolution. But to me, I've always been interested in high frequency data. So I found this data kind of fascinating. And I had an EPA center that began in 2001. And, we had this grand vision that we were going to analyze all of these surface meteorology data and somehow come up with some grand statistical model. And, the main tool that I and others used at that point for thinking about continuously varying spatial quantities was to use Gaussian processes. And I remember looking at the minute by minute winds at the time and just saying, well, that doesn't look Gaussian at all. So I really didn't feel I knew what to do. So I kind of gave up on it, but it's always been in the back of my mind as, really interesting data to think about it from both the statistical and scientific perspective. Okay, so as Reese said, in recent years, I've gotten interested in extremes, and most of my work has been looking at a single extreme quantity at a time. But I wanted, in so many cases, when we look at extremes, we're interested in multivariate extremes. With weather, you'd be interested in both temperature and humidity, or, winds and rain, or temperature at multiple locations, or wind speed at multiple locations. And, there is a lot of work on that topic, but I don't know, something about the approaches that to me seem unsatisfactory. That's not really relevant for this talk. And I thought it might be interesting to look at the wind vector as an interesting case study for thinking about extremes. And that's because it's a vector in the physical sciences sense, not in the mathematical sciences sense, right? It's a quantity with a magnitude and a direction. And I thought that thinking about looking at these data for thinking about extremes might help me generate some new ideas for thinking about multivariate extremes. So, I remembered, oh, well, there's this arm horizontal wind vector data. All right, so what's the data I'm looking at? So these data are within each minute, there's multiple measurements. And so the minute by minute data that gets recorded are the vector means, which are then converted into a speed and direction. But then I'm going to convert them back to northerly and easterly components. Now, what makes these data hard to model is not just their high frequency, but the diurnal patterns is actually quite tricky and quite complex. And because the diurnal cycle is very strongly tied to whether it's daytime or nighttime. And therefore, if you wanted to look at the data throughout the whole year, you would need a model that had a quite complex seasonal diurnal interaction, since if nothing else, the number of hours of sunlight varies quite a bit with season. And so therefore the diurnal patterns have to vary a lot with season. So that seemed like too much, that seemed too hard. So I just restricted to basically 20 days and a few hour period for over 5 years. So I had basically like 101 years of data. And in part, this period of time was picked because there's no missing observations, which makes my life easier. So this is over 145,000 time points where I have this vector wind for each minute. Okay, and I'm going to try to statistically model this. So let's look at some pictures of the data. So here's the data for June 2019. You can see it's a little bit more than 20 days. The gray bars indicate when it's nighttime. So the times here are UTC times. So you got to go back 6 hours to get the local time. And what can you see looking at these pictures? Well, you can see there's a lot of fluctuations on short time scales. Some of these fluctuations are quite sudden and transient, which is the kind of thing that you wouldn't get from a Gaussian process. If you look carefully, you might see that there's more kind of wiggling around during the white spaces than the gray spaces. So that is, there's more short-term variation in the daytime than the nighttime, which I'm sure many meteorologists would say, well, yes, we understand that, that presumably the presence of the sun creates turbulence near the surface that creates this greater variability. But it's not that the winds are stronger during the day than night, it's that the short-term volatility is higher. So this is 1 year, let's look at the next year. So here's 2020, and now we have something quite interesting. If we have this pattern, very strong pattern that repeats for about 7 days. First of all, there's this 1.5 day period here where the winds kind of go crazy. And then there's this very, very repetitive pattern for about 7 days, especially if you look down here, right? It's really a very similar pattern in both the overall trend and the volatility in terms of what happens at day and night, but then it breaks down and kind of heads into something else. So those are some of the things that we might want a model to be able to capture. Here are just the marginal wind vectors by hour over the entire data set. You can see there's so these weird blobs here that stand out, these are all from this time period. So all those things that stick out by themselves are all from a single event. And you know, you can actually see the blob drifting, which is the winds kind of, the winds stay strong, but they kind of rotate over this event. And all right. And now, so the data are very strongly correlated, so it's natural to look at the first differences. And here's the first differences in the wind vectors by day versus night. And you can see they're all on the same scale, and the blobs are much bigger. So the ends are where we're nighttime. The blobs are generally much bigger in the daytime, especially in the afternoon, than at night. On the other hand, though, you know, the most extreme points right here, if you look carefully, there's a point right there. I think that's the point, a point with the strongest, I guess, westerly wind. No, that would be a strongest southerly wind. You know, so while the overall variability is much bigger in the daytime, you can actually get the strongest winds at any time of day. You can also see that the shapes of these distributions change a little bit. Right, during the daytime, these blobs look pretty spherical, but here's an hour where it looks like there's some negative correlation. And so for several of these hours, it looks like there's a predominant northwest to southeast axis for the wind vectors, whereas in the daytime, it looks pretty spherically, directionally symmetric. Here are just the median. So you look at each 10-minute period over the 24-hour day, you look at all the data, and then for each year, so this is 2016, these are 2019, these are the medians of all those measurements. And, you know, so the diurnal cycle in the median winds is fairly weak, and it's not very consistent from year to year, right? It varies a lot from year to year. So it's not, I mean, it looks like there's some kind of persistent trend, right? There's some commonality in these curves and some commonality in these curves, but we need to be very careful about saying something about, you know, a diurnal pattern in the medians of the winds, because there's just so much variation from year to year. And of course, the fact that these, you know, these points are next to each other are largely just a sign of a strong correlation in the data, not that we're necessarily seeing a coherent pattern. All right, so now here's the same for every 10-minute period of the day. Here's the same thing for the interquartile range of first differences. So these first differences are much less correlated than the observations themselves. So we should expect much less randomness in these pictures. And now we see a very strong pattern of much less diurnal variation at night, and then quite strong transitions at sunset and sunrise. And then, you know, it increases up to here. And this is, so these would be kind of mid-afternoon. And then as the sun starts going down, the volatility goes down again. And it's a very similar pattern for the northerly and easterly components. So any model that we come up with is going to have to mimic this. And what these are correlations of first differences. So the black points, so N's are northerly and E's are easterly. The black points are the correlations of the first differences. They're mostly negative, which is kind of what you would usually expect, because I mean, usually when you take first differences, unless the process literally kind of explodes over time, which it shouldn't, because winds are somewhat contained within a range, usually expect first differencing to over difference and create some negative correlations. And so you get these modest negative correlations. The red points are correlations in the absolute differences. Okay, so those you might normally expect to be pretty weak, but they're quite strong, especially during the nighttime. And this is evidence of stochastic volatility, which comes up all the time, for example, in finance applications. But it's pretty interesting here that it's such a strong effect, that well, you have to be careful. I mean, these are correlations, so it's normalized, but there's more changes in volatility at night than in the day, is what this is saying. So that if you're in the nighttime, and if the wind vector has been changing a lot recently, it's likely to keep changing a lot. All right, and if it's been changing very little, it's likely to keep changing very little, which is what creates those correlations in the absolute values of the first differences. Okay. Like I said, I started out hoping this would be good data for extremes. So let me say a little bit about extreme aspects of these data. So it's only 101 days of data, so it's not really suitable data for extremes. The highest wind speed that was recorded here was nearly 20 meters per second. And just once I'll convert to miles per hour for those of us who aren't so familiar with wind speeds in meters per second. So a pretty strong wind, but nothing, really, really strong. Now the wind vector can actually change a lot from minute to minute. It usually changes only a little bit, but there was one instance where the wind speed changed by 7.5 meters, and another instant where the wind vector in 1 minute to the next changed by over 13 meters per second. So that's a huge change in the wind vector from 1 minute to the next. Another feature of the data is that at least the recorded wind speed is on several occasions exactly 0. Now, whether that's because the instrument has some minimum sensitivity, or whether there really is such a thing as, in some sense, essentially exactly calm winds, I'll let people who know about the instrumentation more tell me about that. So there's 640 minutes in this whole period where the wind speed was recorded as 0. So this is the average over a minute. And then and they come in 81 streaks, and those streaks are either 1 minute long, and the longest one was 89 minutes. So there was one 89-minute streak where the wind speed was 0. Now, most of these occur during the night, but not during the day. But there are some during the day where there were 0 winds during the day. Okay, so in terms of the extreme winds, well, none of them are really extreme. And 73 different minutes, the winds were greater than 17 meters per second. But almost all of those occurrences were in that one weird event that I showed you before. All right, so these data really aren't the right data for extremes. If you go to a nearby site, a nearby location, Wichita, Kansas is about 70 miles away, sorry. And you look at the wind records for June, there was, over a period of 49 years, there was a wind speed of 37 meters per second, so almost twice this. So clearly, wind speeds much greater than this are possible. And even, of course, wind speeds much greater than this are possible, because this is right in the middle of Tornado Alley. The 1 minute average wind speed wouldn't even actually make sense. Vector wind speed wouldn't even make sense for a tornado, but in any case, the wind speed's a lot higher than this in a tornado. So this isn't really the right data set for looking at extremes or for any kind of long range dependence either. It hopefully, though, is good data for looking at high frequency variations. And here's just a close up of that one weird event. Here's every 10 minutes for about 9 hours, and the wind speed is staying around 17 meters per second during the whole time, but it's rotating like this. So that would be another tricky feature that one might like to capture. But from the statistical perspective, it feels dangerous modeling these kinds of things, because this is basically one data point, right? There's only one event like this. So for learning about this event, right, you're totally dependent on this one time period for learning about it. All right. So that's some background on the data. Any questions or comments about that? All right.
So, Michael, do you have a sense of how much above the ground the wind speed?
So these are
is
surface winds, so these are presumably 2 meter winds, I think.
2 meters above the
I think
ground.
these are 2 meter winds. Yeah, right. So obviously the winds get stronger as you move away from the surface. There are instruments there that measure winds at higher altitudes, but this is part of the surface meteorology network. So if I'm not mistaken, these are the 2 meter winds. Anything else? Okay, so I've set myself the goal here. So usually when people look at time series data, they're interested in forecasting. I don't know who's interested in 1 minute ahead forecasting of winds. If you wanted to do, even 6 hour ahead forecasting, I think you would want to look at some regional measures of meteorology. You wouldn't just look at this one data set. So I'm going to set myself the task of producing a model to simulate winds. So stochastic weather generators are actually pretty popular in engineering applications where people want to have some ways of generating lots of realistic looking data that they can then stick into their engineering models for looking at something like weather impacts. So stochastic weather generators for precipitation have been around for many decades, and people try to use them for winds too. But this is going to turn out to be a very challenging goal, but I'm going to try. Okay, so when might someone be interested in the wind vector? So obviously there's a lot more papers that people look at wind speed rather than the wind vector. And obviously interest in wind energy has produced a lot of interest in looking at wind speed on fairly short timescales. But even the papers that I've seen that claim they're interested in high frequency wind speeds, usually they're not looking at things fast at higher frequencies than 10 minutes. And they're often looking at hourly. So I don't know. I mean, maybe the wind vector is conceivably of some relevance for wind energy because the wind turbines can't pivot instantaneously into the wind. And so maybe quickly changing wind directions have some small effect on the wind energy, but that's probably not that big a deal in most cases. I'm pretty sure that wind direction matters for aviation, right? In terms of takeoff and landing of planes. Obviously the wind direction matters and not just the wind speed. It's clearly relevant for air pollution dispersal, right? The wind direction clearly matters for that. I would hope that maybe some of the statistical features that I've seen here might get some meteorologists thinking, well, that's maybe worth trying to understand why that happens, because I do think there's a lot of interesting features in these data. All right. And so could I get away with just using any existing time series model? Well, I'm not particularly an expert in time series, but I think the answer to that is no. I think there's too many kind of weird features here that, all the models I'm familiar with or tried looking at just didn't seem to really have any realistic way of capturing all the things I see in these data. And the thing that I have to be what makes this problem hard is that I'm going to try to come up with a model for saying what happens from 1 minute to the next, because after all, once you get a starting value of a time series, if you can come up with a model that describes how the process evolves from minute to minute, you should be able to use that for simulations. The problem is that if that conditional behavior is even a little bit wrong, when you use the model in simulation mode, really bad things can happen. All right, and then I need to have a model that I can actually fit and I can do the optimization problems with. So I have to be careful about how crazy I make the model or how much programming it takes to fit it, because I've done this work. There's no collaborators here. I've done this completely by myself, which is probably a mistake, but it limits how much programming I can do. So, all right. So what is my model? So I'm going to model in 3 stages. I'm going to first model the conditional median of each wind component, and then I'm going to remove those conditional medians, and then have a kind of residual series, and then model the conditional spreads of each wind component. And I'm going to use quantile regressions for this procedure. Okay, so a very common time series model would be that once you adjust for the location and the scale, so the conditional median and the conditional spread, that what you have left are independent and identically distributed normalized residuals. That'd be a very common model in finance so the simplest models wouldn't even include part two. We just have something like this, and then the innovations being IID Gaussian. But finance people are constantly modeling conditional spread, and then they usually assume that the errors, once you correct for that, are identically distributed. But that's going to turn out to be clearly untrue here. So we're going to need to deal with that. So the first thing I was doing, I wanted to really have a fully parametric model in the end. So I tried, because these distributions were fat-tailed, I tried coming up with describing them by a bivariate T distribution where both the degree of freedom and the dependence parameter of the bivariate T would have diurnal cycles. And I worked with that for quite a while until I concluded that just really wasn't adequate. And I'll show some figures later that will, I think, show that. So then I switched to using empirical innovations. I have 145,000 data points, right? So I should be able to fit distributions just empirically pretty well. I've also looked at whether I should smooth these empirical distributions, which I think is worth considering, but I couldn't, to the extent that I tried it, I couldn't show that it obviously made things better. So I gave up on that. So my innovations are going to come from empirical distributions. So I'm first going to try to describe the model. And it's got a lot of components to it, so I'm gonna have to go through it fairly quickly and then try to explain where I got it from. Okay, so I'm gonna do things backwards. I'm gonna say, here's my answer, and then try to say where I got it from. Okay, so like I said, one of the main things I have to deal with is these diurnal cycles. And so that means that, you know, if I have AR coefficients, for example, if I use some kind of autoregressive model, I'm going to need at least some of my autoregressive coefficients to vary with time of day. And it just seemed very hard to, at least given the way I'm doing the data fitting. So part of what I'm going to return to at the end is, should I have been doing this analysis in this kind of very labor intensive way, or would I be better off doing something more automated? That I wanted this kind of the same form for the diurnal interactions wherever they appear in the model. So all of my diurnal interactions use these functions plus a constant function as my basis function. So there's this piecewise linear function that has its kinks at basically sundown and sunrise, so that the function looks simple during the night, right? Because after all, nighttime is always nighttime in terms of solar radiation. And then these kind of cubic spline basis functions for the daytime with an extra knot near sunrise and sunset to allow for complexities that seem to occur near those hours. So whenever I use an interaction, this is how I'm going to try to a diurnal interaction. This is how I'm going to try to capture it. Okay, so ft-1 is just all the past. And so I'm going to try to quantify. So this is a model for the conditional median of the northerly component of the wind vector given the past. And there's a similar model for the easterly component. So there's a part that there's kind of fixed coefficients that allow for a kind of unconditional diurnal cycle. And then there's all these other terms. So there's linear, so I'm going to go through them individually, so I'm not going to really go into the details now. But let's look at the model. There's 34 parameters in all. 32 of them are linear, and then there's 2 nonlinear parameters, this delta and these tau. So I'm going to go through these. Okay, so this term is to try to allow for an unconditional median, but it is not itself even approximately the unconditional median of the time series. If you want to include location parameters in the time series, you really need to subtract them from these terms n wherever they appear. And that's not what I'm doing, because it just didn't seem to help, and it made the fitting much more complicated. So I spent a lot of time trying to do that, and I gave up, and I just used this simple form of trying to account for a diurnal cycle, but don't expect this itself to be the diurnal cycle. Okay, and the next term. Okay, so these are basically AR1 and AR2 coefficients that all vary with a diurnal cycle, all right? And then, you know, when I was looking at AR model, I kept finding if I went to AR3 or AR4 or AR5, they kept fitting slightly better. So often when it looks like you need a huge number of AR coefficients, people find it helps a lot to add one MA component to the model. But I didn't know how to fit an MA model using the programs that I had that would allow for using regression quantiles and would allow for these weird diurnal cycles. So I kind of forced it into an AR component. So the way MA components to a model work is if you invert them and turn them into an infinite length AR model, you see that what you get is that you get the AR coefficients decaying exponentially. So that's what this delta is for. So it's meant to mimic the effect of an MA component. And then this also has so that's this next term here. So this delta is meant to mimic what happens with an MA component, and then it gets multiplied by something that also has a diurnal cycle. All right, that doesn't turn out to be enough. So this term, it doesn't matter much, but I thought I would include it anyways. This is the effect of the most recent easterly wind on the northerly wind, and it seems to help a little bit, but not much. These two terms are nonlinear AR effects. So this arctan of n over tau is a nonlinear effect. So as tau goes to infinity, this converges to just a linear function. But this is the kind of thing, if you're just doing one step ahead prediction, it helps moderately, but maybe not hugely. But in simulation mode, if you leave something like this out, you get nonsense. And then this last term here is a kind of MA-like term in this nonlinear effect. All right, so that's the model for the conditional median. Let's take a breath. And then I have a somewhat similar model for the spread. So I subtract off these conditional medians, and then the way I'm going to model the spread is that these residuals from the conditional medians look fairly symmetric. So I thought in terms of measuring spread, I could take the absolute values and use a quantile regression on them as well. But I decided to use the 0.9 quantile here, in part because I'm more interested in getting the more extreme quantiles accurately, but also because I want to make sure I don't get any negative spread estimates. And so looking at bigger quantiles makes that less likely to happen. All right, so there's this complicated model. Again, I'll go through all the terms. It has 29 parameters, these 26 phi's. Arguably, in some sense, all the parameters are nonlinear because of the way the phi's multiply each other, and I'll talk about that in a second. There's also these two nonlinear parameters here that are mimicking this MA component, and then a nonlinear parameter that's controlling this effect, which I'll explain when I get to it. Okay, so I have a multiplicative term. So this is the variation in volatility that's just a purely diurnal cycle. So there's nothing random about this. And this is the stochastic volatility. So I'm saying the total volatility is in some sense the deterministic diurnal volatility plus times the stochastic volatility. And it's important that those multiply each other in terms of getting anything sensible. If you add them, there'd be no way to get anything that approximated the truth and avoid negative values. So, okay, so this is this term that I'm calling dVn of the minute. So this only depends on the minute. So m of t is the minute of the day. And so this function is periodic with period 1 day. All right. So that's this dVn. Everything else in these square brackets is this stochastic volatility. All these other terms have random variables in their expression. So they're part of the stochastic volatility, and the total volatility is their product. Okay, so this is a AR1 that varies diurnally. These are AR2 and AR3 that don't vary diurnally. This is this MA-like term that doesn't vary diurnally. This is a term for an AR1 term for the most recent absolute normalized easterly component. But so when you're looking at just the medians, each component could almost be modeled separately from the other without really much loss. But in terms of the volatility, each component plays actually explains a fair amount of the volatility in the other. So this term is much more important than in the model for the conditional medians. And furthermore, it looks like the past lags of the easterly absolute residual also are important. So this is so this one here is an MA-like term in the further past lags of the easterly component. Now, another thing that we have going on that I've kind of mentioned indirectly is that when you get very low winds, the volatility is often very low. So in particular, if the winds get to zero, sometimes the next wind is zero. And I don't really want to model that becoming zero or not zero. That seemed to be a complication that was going to be difficult to model and not that interesting. I'm not sure that anybody's all that interested in when the winds are calm versus very light. Although maybe if someone were very interested in that, that could be worth modeling. Okay, and so this is a nonlinear effect. So the bigger sigma is, the more this function flattens out quickly, and this can kind of control whether the wind effect, once the winds get fairly large, it doesn't seem to have an effect on the volatility. So this kind of controls that turnover, and this term also has a diurnal cycle to it. So again, because this problem occurs much more at night than during the day. Right. So those are steps 1 and 2 of my model. So if you thought that was complicated, step 3 is even worse, and I'm not going to really be able to explain all of it, and I don't. So okay. So I have these. So these are these innovations which are, you take out, so this takes out the conditional median, then you divide by this conditional scale, and you get these 2 innovation components. And I'm going to put this O here to emphasize that something's observed, because I want to talk about the observations, but I also want to talk about how to simulate. So I'm going to need to distinguish between observations and simulations. I'm also going to need the residuals that are only normalized for the fixed diurnal variability and not for the stochastic variability. So what I was hoping when I switched to a sampling scheme for getting the innovations was saying, look, I've corrected for conditional location, I've collected for conditional spread. I still know that these innovation distributions depend on time of day, but maybe, suppose I'm at 4:20 p.m. I can just look at some small window around 4:20 p.m. over all the days I have and just sample from those, right? That maybe once I've corrected for the conditional mean and the conditional spread, that there's really just a fixed diurnal cycle in the innovation distribution. But that just turns out not to be true. So this is a plot for the observations between 6 and 7 UTC. So these are the middle of the night, like midnight to 1 a.m. This is some measure of this, the total stochastic volatility. And then here's the northerly and the easterly innovations. So you notice these weird things here. Those are mostly when the wind speeds are either 0 or very near 0. But there's also then, these hugely big kind of outliers, and even the things here. The things that would cause trouble in simulation mode is, suppose I sampled this innovation, and then I sample it at a time when the stochastic volatility is out here, right? These innovations when they get turned back into an actual change in the wind vector, the innovation gets basically multiplied by this number. And if I multiply this number, which is about 15 by 10, I get 150. So I'm saying that the wind vector is going to change by 150 meters per second. That's not really going to work. So I really need to do some more stratifying of the innovations before I can do this sampling scheme. Well, do I really want to say what any of this is? I mean, so I'm not really happy with this. I've stratified the innovations in lots of ways to try to do what? Again, if all I want to do is 1 minute ahead forecasting, all these different methods give very similar answers. Where they give tremendously different answers is when you run the model in simulation mode. So I would try something, it would look pretty good in 1 step ahead prediction mode, and then I'd run a simulation and I'd produce something ridiculous. So I would try again and try again and try again. So this is where I am right now. I'm not entirely happy with it, but at least it doesn't produce anything too ridiculous. And do I even want to explain it? So one of the things I had to do is, suppose the wind vector is already big like this. the wind vector, the next wind vector might go this way quite a bit, right? The winds might weaken quite a lot, but they shouldn't go this way a lot. They shouldn't, you can't, it's hard to go from a big wind to a much bigger wind. And so when I sample winds, I need to keep sample innovations. I need to keep that from happening. And so I applied a rotation that I don't really want to go into. I rotated my innovation vectors to keep that from happening, since it doesn't seem to happen in the data. So whatever direction I take for my innovation, it can't, if the winds are strong, it can't say the winds are going to get much stronger in the next minute, because that doesn't seem to happen. All right. So now I want to use this. So now I have a model in some sense. It's partially empirical because the innovations are sampled empirically. And I have to find some way of sampling from it. Okay. So, I mean, I basically just have to undo the fitting procedure, but I can get multiple simulations of conditional simulations of the future by just simulating multiple innovation vectors. So I can either do multiple conditional simulations, or I can do multiple unconditional simulations. The unconditional simulations, I just need some starting values, and I could just make those up, or I can use some of the data for his things. Okay. So let me try to say briefly where I got this from. So I tried as much as possible to use linear quantile regression, and this is in part because the QuantReg package in R has a method that works very fast. So even though I have lots of, if I have like 30 linear regressors and I have 145,000 observations, it fits the regression coefficients in about a second. And this is important because every time I add a nonlinear parameter, the way I did this, rather than trying to fit all the parameters at once, I did a nested optimization where the nonlinear parameters only get optimized in the outer loop so that they don't have to get changed so much. So every time I add a nonlinear parameter, I make things worse. So I wanted to have as many linear parameters as possible, which explains some of how I did my model choices. I think I need to skip some of the rest of this. I did look at, so quantile regression has a criterion function for the medians. It's just the sum of the absolute deviations. So I did look at that criterion function, and that played partial role in whether I included a term or decided not to. I also looked at what are called continuous rank probability scores on 1 minute ahead predictions. That's a standard way of evaluating predictions. But I also then, once I did all these things, I simulated under my model, and I tried to look at whether the simulations look realistic. So literally the first model that I fit, that I decided, well, that doesn't look too bad. Maybe I'll try running it in simulation mode. That model literally produced wind speeds larger than the speed of light. Not just larger than, you might say, oh, larger than the speed of sound, no, larger than the speed of light. And, that sounds embarrassing, but in fact, for 1 minute ahead prediction, that model wasn't too bad. And it's what happens when you have these kind of complex models with very strong short range dependencies, that if the model's even a little bit wrong, it produces the weird thing. So that very elaborate innovation distribution sampling scheme is meant to avoid producing unconditional simulations with crazy wind speeds. All right, so in building a model, models should be as simple as they can be, but not simpler, right? So I try to have a mix of complexity and simplicity where I measure those things in a heuristic way, as opposed to what a machine learning algorithm, which has some kind of criterion function for what it means by complexity versus simplicity. So I have lots of interactions, but they all have the same form. I have nonlinear AR terms, but they all have very simple and analogous forms. I have, the same basic functional forms for the northerly and easterly components of both the conditional means and spreads. The sampling innovation scheme, it's pretty elaborate, but it was kind of developed in a fairly kind of informal ad hoc way. All right, so in principle, so my model looks back 240 minutes. So to find the conditional distribution of wind at 1 minute given the past, it uses the last 240 minutes. So you could imagine some nonlinear model with 240 regressors. If you stuck this into some some neural net, it would say that, oh, I'm going to come up with a model with thousands or millions of parameters or something like that. And it would have to have some sense of regularizing, but it wouldn't make any of these choices. I'm not saying it would make worse choices, but it would make different choices. All right, so here's just some description of the outputs. This demonstrates the nonlinearity. So this is the AR1 effect. And because it's nonlinear, the effect depends on the wind speed. So this is the AR1 effect when the wind speed is 1 meters per second. The red curve is the AR1 effect for the northerlies when the wind speed is 3 meters per second. And here it is when it's 10 meters per second. These curves are all parallel because that's how I made my model, not because the truth would be exactly parallel like that. All right, so there's a pretty substantial diurnal cycle in this AR1 effect. Here's the same thing for AR2, and here's an attempt to do it for that MA-like term. Okay, so if my normalization scheme, if my first two steps work okay, even though the innovations are not IID, they should be close to uncorrelated, and so maybe I can look at spectra of these. So I have 5 years of data. So these are the averages over the 5 years of the completely raw spectra. So these should look flat. They look pretty flat. There's maybe a little bit more mass here than here. And there's these noticeable, but not huge spikes at the very lowest frequencies. Here's the northerly and the easterly component. And here's the same thing for the absolute innovations. And these look quite good, except again, for this little spike here, this is the easterly. This looks pretty flat to me. So what if you exclude the stochastic volatility? What if you just have the diurnally fixed volatility? Then you get this picture. Okay, well, this isn't even close to flat. So you really need stochastic volatility in this model, and putting in the stochastic volatility as I did, pretty much removes all of this effect. All right, here's the unconditional diurnal volatility by 10-minute period, and the black curve is the fitted, and that fits quite well. These should be uniform. These are the ranks for the 1 minute ahead. So when you simulate 49 times and then you compare the data, the actual data should be equally ranked from 1 to 50. So these should all look flat. These look pretty good. During the nighttime is a little bit off here, but not too bad. So the 1 minute ahead predictions are pretty good here. So now I'm going to compare just simulations of the versus the observations, and I'll try to go quickly. So here was the 2019 again. Here's a simulated 2019. It shouldn't look like this at all. It's just used the last 4 hours to get the starting values. It should, but the hope is that it looks kind of, that if I didn't tell you which was observed and which was simulated, you wouldn't know which was which. That's the kind of thing you should be thinking of. So here was 2020. And there was this very repetitive pattern. I don't think my model can do this. I think I could run my model in simulation mode 1,000 times and I wouldn't see a year that looked like this. So this is just something that's a longer term pattern that's just not in my model. So here's the simulated 2020. Here's the hour by hour things. Here's the observations. Here's the simulated. I don't know, does it look qualitatively similar? Maybe. Here's the observed first differences. Here's the simulated first differences. They're pretty good. There's some weird little features here that bother me a little bit, but maybe I'm being too picky. So maybe I'm actually doing okay here. Here's these 10-minute medians for the observed. Here's for the simulated. I mean, they're not the same, but it's not so clear how much of that isn't just noise rather than something real. So I don't know how that's doing. Here's the observed for the interquartile range of the first differences. Here's the simulated. It's pretty good. It's arguably, it's arguably a little bit different in nighttime for the northerly, right? There's this kind of curve up, but I'm not so sure, because if you actually look at years 6 and 9, they also show this curve up. Which years are that? 8 and 9. It's just like 2016 is this really flat year. So maybe it's doing okay there too. Here's these correlations of the first differences. These are the correlations, the absolute values of the first differences observed. and simulated. The black ones, I think, match very well. The red ones, there's this flatness here that's not in the actual observations, but pretty good. So, not bad. So I'll try to finish in like 5 minutes here at most. So I haven't done, other than just informally, I haven't done any uncertainty quantification. I haven't done any hypothesis testing. I haven't done any confidence intervals or standard errors. And in principle, I could try to do that, but I literally fit hundreds of different models, for each stage of what I was doing. And so I don't know how to correct for, so I've been doing here a giant fishing expedition. I don't really know how to correct for this at all using these data. So I don't even think it's helpful to try. I think if I'd had more than 5 years of data, it wouldn't have been completely crazy to resample years, but that still wouldn't account for the uncertainties due to all the model selection that I did, right? If I conditioned on the chosen model and I did all 29 years of data rather than 5 years, then resampling of years might be reasonable, but it wouldn't do anything about all the fishing I'd done. So I really think that the right way to do uncertainty quantification here is to do everything on a training data and then eventually look at the other years of data. But I don't want to look at the other years of data until I've given up on modeling, and I haven't completely given up. So I haven't looked at any of the other years of data. But I think that'll be the right way of saying whether these model fits are actually, to what extent they're capturing something real as opposed to something just noisy. All right, so, I spent a huge amount of time on this. If I'd known how much time I was going to spend on it, I probably would have never started it. I think, though, that I learned a lot about thinking about complex time, non-Gaussian, non-stationary time series. So hopefully, at least for my own growth as a statistician, it was helpful. But could someone have used some fancy machine learning approach, like some really involved recurrent neural net, and done almost as well or better with much less effort? I don't know. I mean, I haven't tried, so I can't really say. I mean, I did try looking at some packages that claim to do neural nets on time series, but they seem to be focused on purely one step ahead point prediction, whereas I need at the least conditional distributions and stochastic volatility. So maybe there's something out there that could do it, but at least it's not some simple R package that someone like me could just pick up and start using. So, I don't know. I mean, obviously this specific problem does not, coming up with a stochastic wind generator for Lamont, Oklahoma is not that interesting, but hopefully one might learn something about meteorology, and that, I mean, I'd be interested in sitting down with a good meteorologist who looks at high frequency effects and saying, are all the things that I've seen here things that you know about and that make sense to you and that, are worth thinking about a little more carefully. So I also think, though, that high frequency models are interesting intrinsically, and that they're coming up more and more in environmental time series, and that we want methods for dealing with those. I do think that if someone did some special purpose machine learning, did some new coding to adapt some existing machine learning approaches, that things could work quite well. But I do think that the criterion function would have to look at more than just one step ahead prediction. It's just too fragile to hope that a modeling procedure that just looks at 1 minute ahead prediction would actually work well in simulation mode, given the complexities of the dependence. But if there's someone in this audience who thinks they could do it and wanted to take it on, I'd be happy to talk to you. All right. Look, despite the complexity and difficult problem, this is still a very, very narrow problem. I mean, I haven't looked at longer time scales. I haven't thought about seasonality. I mean, I've thought about it, but I haven't done anything about it. But clearly there's going to be strong season diurnal interactions that would need to be modeled. And that I think, again, that just letting a machine learning approach let loose without giving it some guidance is unlikely to work well. These are the wrong data for extremes. And then I'm only looking at one site, right? One height and one location, right? Obviously, the wind process, we're interested in it as it varies horizontally, vertically. And frankly, there's a third component to the wind vector, right? There's a vertical component to the wind, which is also very important meteorologically. And so there's a huge amount being left out here. But even this simple data set, my feeling is every time I look at real data carefully, even things that for which seem pretty innocuous, I end up concluding that the standard models aren't right. And maybe that's just the kind of data I look at, but I don't think so. I think that's a pretty common thing. And so I tried to give a lot of plots here. I think diagnostics are of paramount importance in building models here, and that are really worth thinking about, especially for space-time data. What are good diagnostics would help us see the weaknesses of our models? And I think that gets not nearly enough attention. So I'd like to think that this kind of labor-intensive modeling and fitting is important to statistics and will remain important for the foreseeable future. But I do believe that newer methods could either, at least in this case or in similar cases, can improve or at least speed up the process. I mean, this has really been a lot of my time in a way that's been a little bit maybe not the best use of my time. And so to the extent that modern methods can in some sense explore certain parts of model space quickly, I think that could be very helpful for helping a statistician who wants to do a very labor-intensive analysis. Okay, so that's all I have to say, and I'm open to questions.
Thank you very much, Dr. Stein, for your wonderful talk. So any questions from the audience? Please feel free to ask. You can either unmute yourself or put your question in the chat part. Okay, let me ask one question first. So, Dr. Stein, you talk about stationarity and maybe non-stationarity for those wind, like wind speed and wind vector models. That my understanding is we know that there is a kind of limitation for the wind speed. So from my understanding, if you remove the diurnal and seasonal effects, you should expect to get something like the signal looks like stationary process.
Well, but I'm claiming that that's clearly not true for these data. And that's probably in part because it's 1 minute frequency. So that had been what I was hoping, but I think it's transparently untrue for these data. I mean, it's just the distribution clearly has, even after you do these normalizations, clearly has a diurnal pattern and clearly has some complex dependencies that go beyond just even a fixed diurnal cycle. So my guess is it's in part because I'm looking at higher frequency data. It might also be something about this location. Maybe in some locations, that's not such a bad assumption. But I also think it's probably because people don't want to look. They don't want to know that taking out the location and the scale doesn't make the process stationary, because that just then seems too hard.
Yeah, that's a very challenging problem if it goes to non-stationary.
Although it seems so simple, right? Just a bivariate time series, right?
Yeah.
How hard should it be? But
if there is a complex dependency.
If you did many sites at once, just think about how much harder it would be, right? If you had to do the spatial dependence in the wind vector for sites that weren't too far from each other. Right now, you have to think a lot about wind patterns, how wind directions, have patterns around low and high pressure systems, right? And I haven't thought about any of that. So you would clearly want to use some of that information. I mean, a purely statistical model for the wind field at multiple equations doesn't make any sense. It would have to be at least, in some levels motivated by what we know about meteorology. Whereas I think if we're looking at one site, maybe, I mean, it's true. I used subject matter knowledge in very naive ways, like I knew when sunrise and sunset was, but otherwise this is essentially an empirical model. And I don't think that makes sense if you look at the whole wind field over a region.
Yeah. And my understanding is if the model itself is non-stationary, it's hard to guarantee that in a long run, the model will stay within that
Absolutely,
range.
absolutely, that's right. So I don't know that my model wouldn't blow up in the long run. I mean, I've run that last one I run for like 25 years and it never blows up, but I have
That's
no
good
idea
enough.
whether it actually ever blows up or not. No, that's right. And in some sense, the question is almost not well defined because I use this sampling method for the innovations, right? But even when I was using a bivariate T distribution for the innovations, I have no idea, that's right, whether my model might eventually blow up. So even when I was producing winds, as I said, you know, the first model I simulated, I got wind speeds greater than the speed of light. They didn't become greater than the speed of light and then stay there. They'd become greater than the speed of light and then return back to zero. And then the next day, maybe they'd get half the speed of light and return to zero. And then the next day they'd go 3 times the speed of light. So it was doing some weird, huge cycle. So it wasn't quite blowing up. It didn't drift off to infinity, but it was effectively drifting off to infinity since winds obviously don't go faster than the speed of light. So,
Yes.
Yeah.
This is a really complex problem.
Or at least for me, I don't know, maybe people with some better ideas about how to think about modeling non-stationary, non-Gaussian, nonlinear time series would have some better ideas. But yeah, I certainly found it challenging.
Okay. Any questions from the audience?
Hi, Michael. This is Migang. I really enjoyed your talk. I have very, very naive questions. So, I mean, I absolutely agree that stationarity is not a reasonable assumption here, but at least some of the things that you described, especially like things happen during the night mostly, but not during the day, or some time of some interval of time, the wind speed becoming exactly zero and things like that. Can part of that be due to maybe data quality issue, or are we quite confident about the quality?
So these, I think so. I mean, so these are experimental weather stations, and I think, you know, I mean, you can never say for sure, but these should be very high quality data. I mean, it was, you know, these sites were set up for this kind of, for research purposes. So, you know, whether the zero winds are really zero or not, or whether there's some threshold but below, I mean, but the lowest non-zero wind was very low. It was like 0.002 meters per second. So it's not like the cutoff is 1 meter per second or even 0.1. It's pretty low, you know, the lowest threshold. And the big changes, could the big changes be something wrong? I can't swear that they're not. But there were no quality, I don't think there were any quality flags during this time period. And, you know, I mean, just think about what happens, right, when a storm passes through. I mean, the winds can change very quickly.
True.
So I'm not sure there's anything obviously unrealistic about those changes. Yeah, but I can't swear to that. I've never talked to someone who's part of the ARM instrument people and say, you know, do you really believe this or not? But as far as I know, you know, yeah.
I see.
I mean, but I want to just something you were saying. I mean, I do want to say though, you know, I am in some sense making an kind of assumption of local stationarity.
Yeah.
That is 12:29 p.m. is not that different from 12:30 p.m. Right? If you have hourly data, that's not all that helpful because there's only 24 hours to the day. And so local stationarity isn't that helpful for the diurnal cycle, or especially if you have 3-hour data, right? It doesn't help that much to say 3 p.m. is like 6 p.m. But there's enough minutes in the day
Yes,
that
right.
there is some value in saying that 1 minute to the next should look very similar to each other. And I'm very much exploiting that in allowing my interactions to only depend on those simple basis functions, right?
Right.
I mean, as opposed to having higher frequency variation in my basis functions. Right. So I am using a kind of local stationarity in time of day. And I am assuming that over this 20-day period that each day is statistically like every other day. And I picked, so picking near the near June, you know, the start of summer, right? The length of the day changes very slowly when you're near the solstices, right? So if I picked like 20 days in March, right, it wouldn't work as well because the length of the day is changing much more quickly in March than in June. And then you would probably want a season diurnality interaction there.
Yeah. Okay. Thank you.